Okay, so we are going to solve some exercises related to the standard normal distribution, the central limit theorem, and confidence intervals. So right here we have these exercises. Let's look at the first one. In the first exercise, it says that we have a standard normal distribution. We know what that is, which is normal distribution where the mean is 0 and the standard deviation is 1. And we're being told that the shaded area is about 40%, 0.4013. So what is the corresponding z value? Well, that value is not going to be positive, so we can eliminate those two answers. And it's going to be very close to 0 because that's almost 50% of the area. So it's going to be probably the smallest number, probably 0.25. But how we do that? Well, the way to do that is we go to the tables. Right, so let's go to the tables. It's a tail, it's a negative tail, so we go to the negative table. We go to the area region of the table. Let me erase this. So we go to the area region of the table. We find the closest that we can get to the value, 4013. The closest that we can get to 4013, 4052, 4013 right here. And we see that the z value is negative 0.201235. So a negative 0.25. So that will be negative 0.25. That value goes in here. Negative 0.25. Right? So that will be the answer. Okay? So that's problem number 1. In problem number 2, let me see if I can make this bigger. In problem number 2, it says that the probability that the variable lies between 0 and 3.1. So for 2, we can do a picture right here. So number 2, we have a standard normal distribution with a mean of 0 and a standard deviation of 1. This is number 2. And we want to find out the probability that the value of the variable lies between 0 and 3.01, right? So the way that we're going to do this is by reading the positive table at 3.1, which will give you all this area, but it's giving you an excess of 50% because when I read the positive table, it gives me the area basically from negative infinity to the value. It is also including this green area, which is not part of the question, and that accounts for 50% of the data. So what we do is we go to read the table at 3.1. Let me do that. The positive table at 3.1, positive table at 3.1, which is 0.9990. Oh no, it's 3.01. 3.01. 3.01, 9987. So that means that this whole area is 9987. So this area is 9987 as a decimal minus 0.5, which is this part right here. And that gives me obviously 4987 right here. So the answer is B. So this area is 4987. It's about 49%, 49.87%. So that's problem number 2. So we got the answer to that. All right. Let's look at problem number 3. And in number 3, we say that the probability that the variable lies between negative 0.55 and 0.55. So in problem number 3, see, we're talking about a variable that has this distribution that is standard normal, that means 0, the standard deviation is 1. And we want to know what percentage of values of the variable lie between, what are the two values in 3? Negative 0.55 and positive 0.55. All right, so how we can use these positive and negative tables to find out this area right here. So one way of doing this is that if I read the positive table at 0.55, it gives me all this area, all the area below that particular value. And obviously that area is going to be more than 50%, but it's too much. So what I could do is I read the negative table at negative 0.55 and take the difference of the two numbers, because then I get rid of the excess. So let me go to the positive table. The area below the z value 0.55 is equal to C value 0.55 in the positive table, 0.501234 7088. 7088. So this whole area is 7088 as a decimal. The area below negative 0.55, which is this tail, which I need to subtract from the area below 0.55, which is all this, to get the area that I want. I have to read that in the negative table. So let me go here and read that from the negative table. So negative 0.55, negative 0.55, negative 0.12345, that will be 2946. Negative 0.12345, 2912. 2912. So that's 2912, and the difference between these two, which is the blue area, which is what I want, will be the difference between those two values, which is 0.7788 minus 0.2912, and that gives me 0.48. We need to get another pen. 4876. All right, so this is problem number 3. Do we have that answer? 4876. So we are making a mistake. So let's see what is the mistake right here. So problem number 3, it says that we want to find the area between these two values. So we say 0.55 and negative 0.55. So if we read the table value at 0.55, read the table value 0.55, what is that again? So 0.55. So I read the values wrong. 0.501234, that's 7088. 0.55, 7088, right? 70, I am so sorry. So this number right here, I wrote it wrong, is 7088. So making errors is okay, because then we have to check. 7088. Let's assume that I got this one right. So now the answer will be 0.7088 minus 0.4876, and I get 0.7088. I hope you're doing these calculations with me. So I get 0.4176, 0.41. So that's 0 to us, 4.176, which is A. Okay, so we have to be careful reading the tables. It's because I am changing the screen to where the table is, and that sometimes I don't remember the number, but that's what it is. Okay, so that's problem number 3. So now let's look at problem number 4. We got the answer to 3. So now let's look at 4 right here. We're going to solve this one. And in problem 4 it says that assume that S is normally distributed, find the indicated probability. So in number 4, so now we have a variable that is normally distributed with a mean of 60. That's a population mean of 60. Standard deviation of 4. And then we say find the probability that the value of the variable is less than 53. So 53 is to the left of 60. And the percentage of values that are less than 53 is the same as this area under that density function. Now how we find that area? Well, we know that what we have to do is standardize the graph. We do that by finding the z-scores, converting this into a standard normal distribution by finding the z-score of every value. The z-score of the mean is always 0, and the z-score of 53 is going to be a negative number. It's going to be 53 minus 60 divided by the standard deviation, which is 4. That gives me 53 minus 60, that's negative 7 divided by 4. Okay, so let me see what that is. That would be negative 1.17, 1.75, I'm sorry. All right, so now to find that area, I go to the negative table, to the z value of negative 1.17, because basically once we standardize the 53 to 1.75, the area in the standard normal distribution that corresponds to a z-score of negative 1.75 is the same as the area of this normal distribution with this means and this standard deviation. Okay, so let's go to the table and go to the negative table at 1.75, negative table, 1.75, negative 1.701234, we get 0.0401, 0.0401. So this area right here is 0.0401. And that would be our answer, 0.0401, which is B. Okay? So that is only 4% of the values in essence. Only 4% of the values are below 53. That corresponds to about 4% of the data. But that is the answer. Okay, very good. So now let's do problem number 5. This is like erasing the blackboard, so let's erase this. And let's concentrate on number 5. So in problem number 5, now let's erase all these things. Just remember that you can always stop the video. So in problem number 5, we have a normal distribution. They told us at the top, a normal distribution. The mean is for a data set that is normally distributed with a mean equal to 15.2 and a standard deviation of 0.9. And we want to find out the percentage of values or the probability that if we get a random value from this data set, the value is going to be greater than 16.1. So we're really looking for this area right here. Okay, again, the way that we do that, we basically do a standardization of this problem. The 15 will go to 0, and remember that the z-score of x is x minus the mean divided by the standard deviation. So the z-score of 16.1, how far is 16.1 from the mean? But in terms of the standard deviation, 16.1 minus the mean, which is 15.2, divided by the standard deviation, which is 0.9. So this z value right here, corresponding to that x data value, is 16.1 minus 15.2 divided by 0.9 gives me 1. Let me check that again. 16.1 minus 15.2 divided by 0.9 is 1. Okay, 1. So now we want this tail right here. So how we find that tail? If I read the table value at 1, the positive table at 1, what I'm getting is the complement of that area. So I'm getting this area right here. If I read the positive table value at 1, so let's find out what this area is. So in the positive table of 1 gives me 1.0. Gives me this value, which is 8413. So 8413. So this area right here is 8413, 84% of the data. So what is this area, which is the one that I need? It's going to be 1, which is the area under the whole curve, minus 0.8413. In essence, we're finding the complement. We're using the complement rule. So we get 1 minus 0.8413, and we get 1587.1587. About 16% of the values. About 16% of the data is above 16.1. So do we have that answer? 1587, yeah, right here. Okay. Good, let's continue with the solutions to some of these exercises. All right, let's continue. Let's look at this problem number 6, which says that the diameters of balls produced by a certain machine are normally distributed with a mean of 0.3 and a standard deviation of 0.01. What percentage of balls will have a diameter greater than 0.32? So again, what we do, we're solving problem number 7. We know that the diameter of these things is normally distributed. The mean of this data is 0.3. The variation of the data is 0.01. And then we want to know what percentage of the data, in this case the balls, will have a diameter that is greater than 0.32, which is above 0.32, and it's greater, so we're looking for this area. So again, remember, to do this problem, what we do is, oh no, we're doing problem number 6, I'm sorry, problem 6. So what we do is we standardize the problem. The 0.3 will go to 0, and then we need to find the z-score of 0.32, which is 0.32 minus 0.3 divided by the standard deviation, which is 0.01. Now I'm going to use a calculator, even though that's an easy calculation, but I want to make sure that this is clear. So we get 2. All right, so that means that the z-score of 0.32 is 2, and we want this area. So we have 2 ways of getting that area. If we use the positive table, we see that what is the area below a z-score of 2, then that's a complement of the area that we need, so we need to say 1 minus that value. So let's do it. Let's go to the positive table and find out what this area is corresponding to 2. So below 2 we have 97.72% of the values, 97.72. So this area is 97.72. So this area is 1 minus 0.9772, and that is 1 minus 0.9772. That gives me 0.0228, right? And so, which as a percentage multiplied by 100, as a percentage is 2.28% of the data is above 0.32. So do number 7. Okay, problem number 7 says that the amount of snowfall falling in a certain mountain range is normally distributed with a mean of 89 inches and a standard deviation of 14 inches. Oh, look at this. What is the probability that the mean, so we have to be careful here because it's asking for the mean annual fall during a sample will exceed 91.9 inches. So the question right here is, what is the probability? This is number 7. So the question is, what is the probability that the mean of a sample is greater than will exceed 91.8 inches. Okay, so notice that this is the data right here is the mean of a sample. If we put the data in a number line, then what we're dealing is with sample means, right? But what do we know about sample means? That's when the central limit theorem comes in. We know that sample means are normally distributed with a mean equal to the mean of the population that they came from. This came from this population that has a mean of 89. What is different is the standard deviation. The standard deviation is equal to what? In the sampling distribution is equal to the standard deviation of the population where the data came from, which is 14 inches. But then we need to divide by the square root of the sample size, which is the 49 days. And obviously the square root of 49 is 7, 14 divided by 7 is 2. So now we need to work with this new standard deviation. And the question is, what percentage of these samples will have a mean that will exceed 91.8 inches? So 91.8 is to the right of 89. And so we are trying to find out this data right here, this area, this percentage of values right there. So we do like we always do. We're going to standardize this problem. We want a tail. We could read that tail directly from the negative table, or we can do what we do, the complement. So let's talk about those two cases. So let's standardize this problem. The 89 will go to 0. What is the z-score of 91.8? That's 91.8 minus 89 divided by the new standard deviation, which is 2. So let me calculate that. 91.8 minus 89 divided by 2 will give me 1.4. So this area right here, I need to find this area. Notice that by symmetry, if I don't want to read the negative table, the positive table, and subtract 1 from it like we did in the example above, by symmetry, this green area below the tail area in the negative table for a z-value of negative 1.14 is the same as this one. So maybe not visually, but it is the same as that one. So what we could do is go to the negative table and go directly and read negative 1.4 and we get 0.080. So this area right here is 0.0808. So if that area is that, then this area by pure symmetry is the same. So instead of using the complement in this case, we use the symmetry. But you could use the complement. You can find what this whole area is. This whole area is by reading the positive table at 1.4 and subtract that from 1 and you get the same value. If we do that, let's go to the positive table and read the value 1.4. In the positive table, the value of 1.4 is 91.92. So 91.92 corresponds to this whole area in the positive table, but we want the complement of that. We want the area after 1.4. So that will be 1 minus 0.9192, and that is the same as 1 minus 0.92, 9192, that will give me the 0.0808, which is this one right here. Okay. Okay. Let's do number 8. All right, let's do problem number 8. Problem number 8. Okay, so in this particular problem, we have that the annual precipitations in a certain mountain range are normally distributed. That's the population with a mean of 85 and a standard deviation of 14. Again, what is the probability that the mean annual precipitation to the 49 peak years is less than 87.8? Okay, so very similar to the problem that we did, but what is important here is that the probability that we are going to have to find is the probability of a sample, and we want that probability to be less than 87.8. So what are the chances that if we set a sample of 49 random days, the sample mean is less than 87.8? We need a distribution of the sample means, but by the central limit theorem, we know that sample means are normally distributed with a mean equal to the mean of the population that they came from, which is 85, and a standard deviation, which is equal to what? The standard deviation of the population where they came from divided by the square root of the sample size, which is 49, and then this gives me 2 again. All right, but in this case I want less than 87.8, so I am looking for this area right there. Again, I standardize the problem, so I'm converting this into z values. The 85 will go to 0. The z-score of 87.8, of course, is going to be negative. 87.8 minus the mean, which is 85, divided by the standard deviation, which is 2. That z-value is going to be 87.8 minus 80. Oh, sorry. Huge mistake, no? I know some of you were saying, why are you doing that? We need to rewind right here, because we know that the mean is 85. That's what we are told, 85. But 87.8 is to the right of 85, so that's 87.8. And then we want this whole area right here. So our answer is going to be, this cannot be the answer. This cannot be the answer. And the only answer is going to have to be more than 50%. So it's either C or D, okay? So that's a mistake, putting the 87.8 as a lower number than 85. That would be a mistake. So I am glad that I catch the mistake sooner than later. But let's standardize. The 85 will go to 0, and the 87.8 will go to 87.8. Now it's going to be positive minus 85 divided by 2. And that gives me 87.8 minus 85 divided by 2, 1.4. 1.4, which is all this area. All right, so in the positive table, when we go to 1.4, we get 91.92. 91.92. So this area corresponds to 91.92, about 92% of the values. So what percentage of the values? What percentage of sample means? What percentage of samples? So let's write this down so we understand what we did. What we did right here is this. We have this population where the mean is equal to 85, all right? And a given standard deviation. So we're going to take a sample from this population, and now we know something about the sample mean. We know that 92%, about 92% of the samples of 49 units from this population will have a mean that is less than 87.5. So I hope that that is clear. That is very important for quality control, and also it's very important to test hypotheses using something called confidence intervals. All right. Okay, so let's do some more of these problems. All right, let's do problem number 9. And this says that for women aged 8 to 24, the pressure are normally distributed. Okay, so notice right here, 23. So we know that this is about the mean of a sample again. Find the probability that their mean, okay? So we want to find the probability that the mean of a sample is between two values. So the mean of a sample is between, sample mean is between 119 and 122, right? So we have a normal distribution because sample means are normally distributed. The mean is what? The mean is the same as the mean of the population, which is 114.8. We're doing problem number 8. And the standard deviation, remember that you have to adjust it, is the standard deviation of the population, which is what? 13.1 divided by the square root of the sample size, which is 23. We talk about sample size later on. And we want to find out what percentage of data, well, both values are above 114. So what percentage of data is between 119 and 122. So we want this little area right here. So how we do this again? We standardize the problem by doing a new standardized distribution. And remember that the mean always goes to 0. The 119 will go to the z-score of 119. The 122 will go to the z-score of 122, and then we're looking for that area. Okay, so let's find the standard deviation. First, 23 square root. We want the inverse of that. That's 4.79. 4.8, 13.1 divided by 4.8. So I get the standard deviation to be 2.73, about 2.73. So now we find the z-score of 119, which will be 119 minus 114.8 divided by 2.73. That gives me 119 minus 114.8 divided by 2.73. That gives me 1.54. So we got one z-score, which is 1.54. What about the other z-score? Z-score of 122 is 122 minus 114.8 divided by 2.73. That gives me 122 minus 114.8 divided by 2.73 equals to 2.64. That's 2.64. Okay, right here, 2.64. So how we use the tables? So we're going to find the area under 2.64 in the positive table, and that is equal to 2.64 right here, 2.01234, 99.59. So that will be 99.59. And obviously that's too much area, because that is all the area below 2.64. Now let's find out how much area is below, what percentage of values are below 1.59. So we go to the positive table again, 1.5 right here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 94.41. So I'll give 94.41. So the answer is the difference between these two values, which is 0.9954 minus 0.9441, which is 0.0518, basically, which is about 5%. So let's go to problem number 9 and see if we get an answer of 0.0518. 0.05. I don't see 0.0518. This will be the closest, 0.0577. But our answer should be more precise. I did a lot of approximations though, when I did the square root of 23 and so on. Okay, so maybe that's what it was, but I think the answer is this one right here. Okay, well, so let's do this. We have the answer, but I don't like the approximation to be so off. It's not off by very much, but it's still. So let's repeat, let's do the calculations more precisely. So again, and it's good to repeat the problem anyways. So again, right here we have, in problem number 9, we're trying to find out the mean of a sample. There may be another situation that this problem may have been done with a t-distribution, but let's repeat and let's use more decimal places. So right here the question is to find the mean of a sample. So the mean of a sample right here, a sample means happens to be normally distributed with a mean equal to the mean of the population, which is in this case 114.8, and a standard deviation, which is standard deviation divided by the square root of n. All right, so let's calculate this more carefully. Sigma is 13.1, and the square root of 23 is 4.796. Let me use more decimals. 13.1 divided 4.796 gives me 2.73. Is that what we got before? 2.73. So that is the standard deviation. I want to find out how many of the sample means fall between 119 and 122. So we need to find the z-score of the two, 122, which gives me 122 minus 114.8 divided by 2.73. So 122 minus 114.8 equals, divided by 2.73 gives me 2.637, which is 2.64. I need two decimals. Z-score at, this is the Z-score at 122. Z-score at 122. Z-score at 122. The Z-score at 119 is 119 minus 1114.8 divided by 2.73. That gives me 119. 119 minus 114.8 divided by 2.73, and that will be 1.54. All right. Let's see if we can get a better value here, although it seems that we have the same numbers. So the area corresponding to 2.64, the area corresponding to the z value 2.64, the area below those z values is 2.64, 2.61234, 2.601234 is 9959. 2.601234, 9959. And the area below 1.54. So we go to 1.5 and then 4. 1.54, 1.50, 1, 2, 3, 4 is 9382. 9382. And the difference of the two is 0.9959 minus 0.9382, and that will give me 0.0577, which is, oh, it's right there. Okay, so I wanted to repeat the problem. Even though we got the answer, it was a little bit off because of these standard deviations. Notice that I used more decimals here. So that's something that you need to be careful with. To get the precise answer, then you may have to use momentarily 3 decimal places and then do 2 decimal places at the end. Okay, so I am glad that we got that answer. Let's do problem 10. So let's erase this thing right here. We do 10. All right, so in problem number 10 says that the amount that it takes a mechanic to rebuild a transmission for a given car is 8.4 hours with the given standard deviation. So again, the question right here is, what is the probability that the mean of a sample of 40 mechanics that they will exceed a certain amount of time? So in this particular problem number 10, let me make it bigger just in case the quality of the video is not that good. So in this problem number 10, we have we have to find out the chances that the mean of a sample of 40 mechanics have a mean greater than 8.87 hours. We know that the sampling distribution, we have a mean equal to the mean of the population where the sample came from, which has a mean of 18.4 hours. We know that the standard deviation of this sampling distribution is the standard deviation of the population, which is 1.8, divided by the square root of the sample size, which is 40. Right? So let's be careful here because that's where our last problem, some decimal square of 40, square root of that gives me 6.324. I'm going to use that 6.325 for now. 6.325. That is the standard deviation. Now I want to find the chances that the mean exceeds 8.7, so 8.7 is bigger than 8.4, and we want to find out this region right here. So what I'm going to do is I'm going to standardize the problem. Again, the 8.4 will go to 0, and the 8.7, let's find the z-score of that, of 8.7. That will be 8.7 minus 8.4 divided by 6.325. So 8.7 minus 8.4 divided by 6.325, that is small number 0.047, but the table only does 2 decimals, so we have to use 0.05, right? 0.05. We want this area. So your answer should be very close to 50%. This is problem number 10. What problem are we doing now? 10. So yes, we're doing good. So let me erase this. So we're in problem 10. Okay, right here, let me check this. Right here, when we're calculating the standard deviation, I think there is an error there because, let me calculate the standard deviation again. Because the standard deviation, if I divide the 1.8 divided by the square root of 40, which is about 6.4, I get 0.285, right? And if that is the case, the z-value needs to be divided by that standard deviation, which is 0.285, and then that z-value is going to be a little bit large, which is what? 8.7 minus 8.4 divided by 0.285, that gives me 1.05, and so this is 1.05 instead of 0.5, so we need to find this area. If we read in the negative table, negative 1.05, negative 1.0, 0, 1, 2, 3, 4, 5, we get 1469. That this area right here is 1469. 1469. All right, let's check 1469. So problem 10, we have that answer 1469 right here. So what is the interpretation of this? Well, if we were to take a sample of 40 mechanics from this population of mechanics, the chances that the mean of that sample will be greater than 8.7 hours is 0.1469. Or another way of saying this is that about only 15% of the samples of 40 mechanics we have a mean repair time of 8.7 hours, greater than 8.7 hours. Okay, so very good. We have to be very patient with these problems, and that's why I'm doing all the calculations. That way you do the calculations with me while you watch the video. Let's do number next. So in problem 11, find the critical values corresponding to 0.005. Okay, so the next one, which is problem 11, what this really means is that find the z-value in the standard normal distribution that corresponds to an area that is given to you of 0.005. So what is the z-value? And in this particular case is that basically you're going to find the negative, but the positive is going to be the same. They just want the positive one. So you just go to the negative table, find the area corresponding to 0.005 and grab the z-value. So if I go to the negative table, which has too much scratching on, and I try to get to the closest that I can get to 0.05, there is a point, is 0.005, 0.005, right here 0.0051. Oh, there are two values, so they choose the one in the middle. So that would be negative 2.575. That would be, this one would be negative 2.575 and the positive will be 2.575. That is when we're creating the confidence intervals, that we need those critical values to find the margin of error. So in that particular case, this will be the value. In question 12, that would be the same thing. In other words, if we were to have a standard normal distribution, what would be the area below a z-value of 0.36? So we want this area. So no, we know that the area is 0.36. So that would be, what would be the z-value corresponding to that? Even though we're going to get a negative answer, we know that by the symmetry, we are basically one both, but they only write the positive here. So we're going to read in the negative table what, for an area of 0.36, what is the z-value? So for an area of 0.36, right here 0.369, 0.362, the 0.3594, this is the closest. The z-value is negative 0.30123456. Oh, it's the same. So in this case, the value is the same as the area. This is negative 0.36. This would be the positive 0.36 right here. Very good. Let's look at problem 13. All right, so right here in problem 13, same is a question about the mean score. So it's about a mean. We know that sample means are normally distributed with a mean equal to the mean of the population that they came from, and the standard deviation is going to be the standard deviation of the population divided by the square root of the sample size. Right? Let's find out what this value is first. 24 square root, so we get 7.8 divided, I'm going to use 3 decimal places right here, which is 4.898. Well, let me use 98, right? So this gives me 7.8 divided by 4.898, and that is 1.59. So that is that standard deviation. This is the sampling distribution for sample means, and I want the mean of the sample to be less than 70, which is to the left of 73. So I want this area. So now we know what to do. We standardize the problem. The 73 will go to 0. Z-score of 70 is going to be 70 minus 73 divided by 1.59. That gives me negative 1.89. Negative 1.89. And we want this area. So how we find that area? We go to the negative table that corresponds to the value of 1.89, and we want to know the percentage of values below it. So negative table 1.89, 1.8, 1, 2, 3, 4, 5, 6, 7, 8, 9. The last one 0.0294, 0.0294, 0.0294. That's about 3% of the values. So let's see, 0.0294, 0.0294. Okay, so this is another problem that we should, so the answer is this one. Okay, we know why. So the answer is 0.0278. We got 0.029. So you see that the error is really in the thousands. So that's not a big error, and the reason is that these approximations that we do here. So I'm going to leave this problem for you to do the right approximations. All right. Okay. All right. So let's do problem 1 minute. I'm trying to get, okay, let's do number 14. And problem 14 says to find the critical values that corresponds to a 90% confidence interval. So what that means is that if we are going to build a 90% confidence interval, we want this symmetry of 90% around the mean. And so the tails right here are contain the rest, which is 2%. That is usually called the alpha, the level of significance. So that's 2%. Now you see this alpha over 2, because if I divide that alpha by 2, this gives me this one tail, which is 1%, or 0.01. And that's what I'm going to look in the table to get the value, in the negative table. So if I go to the negative table and try to find an area of 0.01, let's see, what do I get? 0.01, 0.01 right here. This is closer, 0. Okay, so this is the closest. That will give me 2.3, 2.30123, 2.33. So negative 2.33, and the positive is going to be 2.33, right? So that will be that answer. So basically we're taking the confidence level, we divide it by 1 minus that to get the tails, and we divide the tail by 2 to get the region, to get the value. Thank you. Okay, so let's do a few more and then we do a new tape because otherwise it get too long. All right, right here, let's find the critical values if we want a 95% confidence level. So 91% confidence level, we take this 1 minus 0.91. What are we going to do with that? What is that called? That is the area in the tails, which is 0.09. We take that 0.09 and we divide it by 2, and we get 0.05, 0.05. That's basically the area in one tail right here. 0.045. So then we go to the negative table. See what is that value? 0.045, 0.048, 0.045, 0.055. Let me erase this. So we want to get the closest to 0.0. What is it? Forgot already. 0.045, 0.04, 0.040, 0.041, 0.042, 0.043, 0.044, 0.045. So we have to choose between two values. I have here 0.0455 and this is 0.0446. So this is closer by 1 unit at the 1000 location. So that would be 1.7. Let's check it to see if we have that answer. So 1.7, do we have that? All right, yes. So that will be the value. Find the critical value that corresponds. Let's do number 16. All right. So in number 16, we want to find the critical value. In other words, if we were to do what type of confidence, a 96% confidence interval, what are going to be these values, the critical values? So again, we find this area right here, which is what? Which is 1 minus 0.96 divided by 2. That will be 0.02. That will be 0.02. All right. Now we go to the table and we want to get the closest that we can get to 0.02. 0.02, 0.022, 0.028, 0.02. This is the closest, I think. This is 2 units, this is 3. So that will be negative 2.001, 2, 3, 4, 5. 2.05. 2.05 right here. That will be the critical values. 2.05 minus 2.05 plus. Okay, so what we did again, we take the 96, we find out how much is in the tails. That gives me 4%. So in each tails I would have 2%. Written as a decimal is 0.02. I go to the negative table because I have the area, then I get the critical value. Remember, these critical values are the ones that I'm going to use in the margin of error formula to create the confidence intervals, if you already saw those tapes. All right. All right, so that was 16. So let's look at problem 17. Let's look at problem 17. Well, I think we already did that, so I'm going to go to 18. Problem 18, what I'm being told is that this area is basically 96%. What is that value? Well, so I'm going to go to the positive table and read in the area section to get the value. So the closest that I can get to 0.9599, 95.99. But now we're in the positive table. 99. So the value was 95.99. 95.99 right here. 95.99. So the value is 1.75. 1.75. Right. Equation D. All right. What I'm going to do is I'm going to stop this tape here. Then I'll let you do 19. Then I will do from 20 because the tape is already 45 minutes and it will take too long to upload. All right. So there will be 2 videos with the study guides, with solutions to the study guide.